I might have to leave class a little early. My son's still sick, my wife's out of town, so there's some logistic issues that I'm gonna have to attend to. So if we leave a couple 20 minutes early or so, hopefully that's not an issue. I don't really have any other options though. It's better than no class at all. So
I don't think there's an issue.
Alright. I just want to make sure that you're,
that hurts us in the long run.
you know, you're getting what you paid for, right? You all paid to be here and to, so I just want to be respectful of that. And also of administration that's be listening.
We voted on it, so it was our choice to send you out.
Class
early.
decision.
Yeah.
Hear that, Everett
CYA. Okay, so homework questions. 8.2, number 6.
That's beautiful. Oh, yeah.
Had a kid last semester who would always talk about politics as a teacher. We like, what do you think about teach? I think Donald Trump is pretty bad. He's like, I want to talk about this.
All right. So 8.2, number 6, integration by parts. Integration by parts helps us deal with the product of two functions. So do we recognize this? We did one of these in class. So what's the deal with a problem like this? Integration by parts, and then what ends up happening?
Eventually, you're going to get to the point where your integration by parts is going to match your original, what you're supposed to evaluate.
Right.
And then you're supposed to add it,
Yeah.
get rid of it, and then add it to the original.
Exactly.
Basically, everything over 2.
Yeah, it depends on how many of them you have. Right. So this integration by part will yield the same integral after a couple of iterations. So we end up solving for the integral. Okay. So we should let u be what? And then that means our choice for dv has to be e to the 7x dx. The one we did in class, granted, was a little bit simpler because we didn't have, arguments like 7x and 4x. So, these things keep multiplying and compounding. Okay, so du, the derivative of u is what?
Negative 4 sine 4x, negative 4 sine 4x.
Right. Negative 4 sine 4x dx. And v? 1/7 e to the 7x. Okay. So let's write the original integral. Is equal to u times v. Minus the integral of v du. So we can just fit all that in there and then reconcile the constants afterwards. So minus 4/7 e to the 7x sine of 4x. So you can either choose to leave the 4/7 in as part of one of these factors, or we could put the 4/7 out front. Just remembering that when we do integration by parts again, the 4/7 is going to apply to both uv and the integral of v du. Right? So does anyone have a preference? Are y'all leaving those in, or are you taking them out? Taking them out? Okay. So we'll have a positive integral 4/7 times the integral. Okay. So integration by parts again with this piece. Let's do green. Similar approach. U is sine 4x. dv is e to the 7x dx. Okay. du is what?
4 cosine 4x.
Okay, good. 4 cosine 4x. And v, once again, 1/7 e to the 7x. We have this. Second. Copy that.
Combine 4/7 with 1/7 in the beginning,
With this one and this one? No, they're kind of like different terms. I mean, we could factor out a 1/7 from all of it, but they're not like terms. Okay, anyway. We have the original integral 1/7 e to the 7x cosine 4x plus the 4/7. And we have all of this being split out. Okay, again, uv. Oops, I'll put the e first like I did earlier. Minus the integral of v du, again, another 4/7 e to the 7x cosine 4x dx. Everyone okay with what we've done? Are there any questions? Okay, so now at this point we notice I've got an integral that's same two functions as I started with. And this one right here. So we just got to determine how many of those we actually have so we can combine them. So now we have those two things as like terms. So we have 4/7 times 1/7. Let's just do it this way. So that's going to be 4 over 49. Then we have 4/7 times this, so we have minus 16/49. Does that look all right? So now we need to add 16/49 of those over here to get rid of that. These together. And left with this on the right hand side. Honestly, we're kind of sloppy with our constants of integration, because each time we integrate, we should get a different constant, C1, then C2. Okay, so then we've got we got 49 49ths plus 16 49ths. What does that give us? 65. So we got 65 49ths of these. Equals to all of that stuff.
So the problem I have with this one on the homework is that the 16/49.
Uh-huh.
Why did you see the comment, like, why are we squaring that? Like, this is 4 times 4 we're squaring.
Because that was actually coming from, let me draw it here in the race. Remember we have the original 4/7 out front of this. We had uv minus the integral of v du, or we had another 4 7ths, right? It was 4 69ths.
Right.
Yeah, so that's where that came from. You're welcome. So we just need to multiply by 49 over 65 on both sides to solve for the actual integral they wanted us to find. Simplify cosine. That's a cosine. 4x. At some point we would have this, we would have some constant here multiplied by the 49 over 65. I'll do a better job of keeping track with the constants, because when we look at chapter 9, 9.1, 9.3, it's important to keep those constants in the mix. And I don't know if my math lab would take that, but if not, it's easy to simplify from there. So does that help?
So it really becomes 7 equals x plus 4x plus 4.
Oh, yeah, my bad. I dropped this 7 here. Yeah. So 7?
So 7 e to the 7x plus 4x.
Yeah, but we have 7 over 65.
Yeah, but then you just multiply it, right? Divide it. Just divide it.
Just put all of it
Yeah,
over
all of it over
65.
65.
Oh, yeah. Yeah, you can put all of it over 65 and just multiply through by the 49, yeah. Any other questions on that? It was A2. Other homework questions from A2? Yeah.
Number 11. So evaluate using integration by parts, evaluate using direct substitution, verify that your answers in part A and B are consistent. When we verify that when we take an antiderivative and we verify that they're consistent, antiderivatives, or if we think about the derivative and checking an antiderivative, we take a derivative. Derivatives can differ by what? By a constant, right? So sometimes can be tricky to verify to see where the constants get absorbed, but we'll see. Was there any part in particular on this, or the whole thing? Just part A.
Okay, part A. Oh, there it is. Yeah. Okay. So if we're doing this integration by parts, how do we want to look at this function?
X times x to the third. And x plus 7 to the 1/2.
product of two functions. And so, this the issue here with our kind of the way we were, at least in our notes, we're told to identify u first by logarithms, etc. Well, we both of these are algebraic functions, right? So which one should we let u be? In other words, which one should we let dv be? Because we want dv to be the largest portion of our integrand that we can integrate. So I haven't worked through this problem. At least on the surface, I don't see any issues with letting u be either or. Because we can integrate x dx and we can integrate x plus 7 to the negative 1/2. But x plus 17 to the negative 1/2 is the largest portion of the integrand that we can integrate, right? Okay, so let's try this. dv equals x plus 17 to the negative 1/2. And then we'll let u equal x. So du is dx. V, the antiderivative of x plus 17 to the negative 1/2, what would that be? Say that again.
2x plus 17, or 2 times x plus 17.
To the positive 1/2 times 2. What do y'all think? So here, we could treat this as a separate problem and do, if you need to, you can do a u substitution. Negative 1/2. So we'll let u equal to x plus 17. du is dx. So this turns into the integral of u to the negative 1/2 with respect to u, right? At 1, it's u to the 1/2 over 1/2. That's it. And so let's see what this turns into. uv u times v minus the integral of v du. Remember the integration by parts, what you should end up with as far as the integral v du should be equivalent or easier than what you started with. Yeah.
Would that first term be x plus 17 as a positive function?
Oh, yeah. Yeah, thank you. That's u times v, thanks. Yeah. Okay. So we end up with the second integral clearly much simpler than the first. So it tells us we probably did something right. So we've got this minus 2 times, again, the integral of x plus 17 to the 1/2 now would be what?
2/3 x plus 17.
Right. Let's do this plus our constant, call it C1. That's pretty much it, right? I don't know if we need to simplify this, or because what you'll notice is if you do part B, you'll come up with an antiderivative that probably looks a lot different than what you have here. So when we're comparing the integral in part B by u substitution versus the one by integration by parts, sometimes you've got to look at either function, simplify one to make it look like the other. So that, I guess, can be a little bit tricky sometimes, but they should differ. questions on this example? Any other 8.2 questions? Other homework questions? I guess we really haven't. We've completed 8.1 and 8.2, got most of the way through 8.3.
Number 4 on page 3. I got 1 on page 3.
It's an 8.3. The 8.2, 11, and 6. Did you end up getting this, Christine, or?
I don't think I got finished with this yet now.
Is that number 6? Number 4, that was 8.3, number 4. I suppose, I'm not sure. I suppose there's a way to rewrite secant so that we could use like integration by parts or something like that. Technically, we haven't talked about integrating secants and powers of secants and tangents yet.
Oh, okay.
So,
That's why I was stuck there for a week.
yeah, I mean,
It's split up to like you secant x times c squared.
yeah.
Or secant cube x.
Right. Yeah. So the idea would be, as we'll see, I think at least this might work. Let's see. Just to take secant to the 4th and rewrite it as secant squared times secant squared x dx. So just like when we dealt with like the sines and the cosines, the thing that we split off to put with dx, that gives us an inclination of what our u substitution should be. Which
Say, we know the integral of secant.
The-
It's straight secant.
right, you know the integral of secant, but what about secant to the 4th?
Can we not use it?
Well, so
You
yeah.
Just change that to 1 plus tangent, right?
So if u is secant, then what's du?
Secant x, tan x.
Right. So we do have this. This is our secant to the 4th power, right? So how do we account for that differential? We're adding layers of complexity that aren't there now. So we split off secant squared. We should let u equal tangent, because that's the derivative of tangent. And then rewrite this in terms of its Pythagorean identity. PYT, Pythagorean identity.
Why can't you just make a whole number?
So like express secant squared as
1 plus.
1 plus tangent squared. So I mean, there's nothing wrong with doing that. I mean, it's totally valid algebraically, but does that help? Like, what could we do with that? There's nothing wrong with writing it that way, but what can we do with that?
You said.
So if you, what would, so u would be 1 plus tangent squared? So the derivative of tangent is 2 tangent times secant squared. So you've got a similar issue with the u substitution from the beginning.
I was trying it as like 1 over cosine root 4. Is that allowed?
Oh, let's see. If we write it as 1 over cosine to the 4th.
Yeah.
And we'd have to express that as 1 over cosine squared. And then we would have to write that as 1 over this squared. So then we have a 1/4. Yeah, so I think this is where the problem is. Cosine 2x squared. So then the problem is we couldn't just look at this as like, if that were our numerator, then we can take the antiderivative of 1 to cosine 2 and cosine squared of 2. But since it's 1 over that, now we're in like a completely different setting. So again, that's a valid thing to do. But once we get here, we look at that and say, well, that's even more problematic than the original. So yeah, it's worth the shot. We gave it a try, but not working out. All right, so I'll not save this because we haven't talked about it yet. Once we talk about it, hopefully that one becomes a pretty easy thing to do. So powers of secant and tangent. Excuse me. N corresponds to the power on secant, and it says if secant is an even power, then we split off a secant squared. Our u is going to be tangent, and then the remaining powers of secant have to be rewritten in terms of tangent using the Pythagorean identity. So if secant's even, that's what we do. If tangent is odd, we split off a secant tangent. Our u substitution is secant, and then we rewrite the remaining powers in terms of Pythagorean identities. If both tangent and secant, or rather if tangent is even and secant is odd, then we have to rewrite the even power of tangent in terms of secant to produce a polynomial in secant and apply reduction formula 4 to each term. So I told you didn't have to remember those reduction formulas, so you wouldn't see a problem where tangent's even and secant is odd on the test. So because you don't need to memorize those reduction formulas. Okay, so we're primarily dealing with these two here. And so the example that we have in number 11, both methods that we've starred there could be applied to this. Because notice we've got a secant that's even and a tangent that's odd. So we'll look at both methods for this one and finish off this section. So the first approach, we see that we have secant to an even power. So then the process there, secant to the even power, we're going to split off a secant squared. Put that with x. Just like with the sine and cosine stuff, what we split off, we put with a differential, and then that tells us what our u substitution should be. Yeah.
Let's say, you remember, say it was secant to the 6, would it be tangent cube times secant cube times secant squared? Or would you have to write that?
Secant squared, secant squared, secant squared.
Or would it be 3 secant squares?
No, if it were secant, so secant to the 6th,
Yes.
so we would leave secant to the 4th and split off a
Well,
secant
yeah.
squared. Yeah. Yeah. Yeah, no matter how high the even power is on secant, we just split off a secant squared because our u is going to be tangent. So we're going to let u equal to tangent. That way du is secant squared x dx. I mean, if you have to, just rewrite what we have just to keep track. So we have tangent cubed, we have secant squared here, and then we have our secant squared x dx as du. So that's kind of what we have accounted for so far in the original. We just have this being our du. But if we go back to our original u substitution, everything else needs to be in terms of tangent. This tangent cube is good. We need to rewrite secant squared. So we're going to leave tangent cubed, secant squared, rewrite Pythagorean identity times du. So secant squared is 1 plus tangent squared. So we have u cubed times 1 plus u squared times du. Any questions on that? Remember these integrals that we see in A3, although they involve trig functions, they're really u substitutions in disguise. We just have to split off the right thing to do that. U was tangent. Okay, so we get u to the 4th over 4 plus u to the 6 over 6 plus c. So, yeah, tangent. So our antiderivative is tangent to the 4th over 4 plus tangent to the 6th over 6. So with trig functions, I think there's one in your homework that has you do integration by parts, and then a u substitution, and then validate that what you, kind of like that last problem we looked at, validate that the two antiderivatives are legit. It's a little harder with trig functions because you have to utilize identity sometimes to show that this trig function is equal to this other trig function. So and that's kind of what we'll see if we take the other approach, where we focus on the fact that tangent is odd. So when tangent is odd, we split off a secant tangent. Is that tangent cubed? So this is going to be tangent squared. So we have secant to the 4th. So that's going to be secant cubed, because we split off a secant times a tangent. here, that's our du essentially. That means our u should be secant. That means we need to rewrite the tangent squared in terms of secant. Secant squared minus 1 times secant cubed times our du. Y'all all right with that? Yeah.
The general principle is you want your du to be equal to what you basically
Split off. Yep, exactly. Now with sine and cosine, it was, we think of it that way, but remember if we have u being cosine, then we'll have negative sine as du, but those constants are easy to move over to the other side, so, but yeah, that's the rule of thumb. So we have u squared minus 1 times u cubed du. So u to the 5th minus u cubed du. So you see how this one's different, right? The one we did previous when we split off at secant squared, it was, what was it, u to the 5th plus u cubed. This one's u to the 5th minus u cubed, I believe. Yeah, see u to the 5th plus u cubed. This is u to the 5th minus u cubed. So we get u to the 6 over 6 minus u to the 4th over 4. Excuse me. And this time our u was secant, so we have secant to the 6th over 6 minus secant to the 4th over 4. So both are equally valid antiderivatives to the same function. Again, one way to check is to take the derivative, see if it turns into tangent cubed secant to the 4th. You probably have to use identities to see that, but we can check this. So, questions on this? That's it. Yeah, the strategy for. Oh, I don't have it. Okay, so the strategy for cotangent and cosecant. That's an N. Oh, they're using a little n, so cosecant to the nth. The strategy for those is exactly the same for the strategy for tangents and secants. So literally you can just cross out tangents, replace with cotangents. I missed one. Process is identical though. And we can scratch out secant and put in cosecant. Oh, I missed a tangent. So yeah. Yeah. As far as I can remember, your textbook doesn't actually have that, which is why I had to do that. Kind of a picture thing. I think that's it. Okay, so that's it. That's 7.3. Do y'all have any questions on that? I mean 8.3, sorry. This is the old 7.3. So 8.4, we've looked at, like, early on in Calc 1, we looked at substitutions, where we explicitly substituted something in that was already present in the integrand. Here with trig substitutions, we take something that's present within the integrand and allow it to equal a trig function. So our substitutions are trigonometric, and we'll talk about that in a moment, like what is the advantage of using a trig substitution. I don't know why I put this here. I hope all of you remember all of this. So this setting that I hope you all remember applied to a problem like number 1 is in every single trig substitution problem. In order for us to convert back, just like when we convert from u back into x, for instance, with our trig substitutions, typically if you're using theta and x, we have to convert back from theta in terms of x, just like we had u in terms of x, we had to convert. So just remind us here, sine is defined as what? The ratio of opposite over hypotenuse, which means that cosecant is the hypotenuse over the opposite. Cosine was adjacent over hypotenuse, reciprocal, secant, hypotenuse over adjacent. Tangent was defined as opposite over adjacent, which means cotangent is adjacent over opposite. Okay, so given the fact that sine of theta equals x over 8, draw a right triangle to determine the value of cosine, assuming that theta is in between 0 and pi over 2. So here's theta. We're given the fact that the sine of this angle is x over 8, so opposite. This is our hypotenuse. And then we need to figure out the base of this triangle. What's the length of the base? Yeah. Close. You're kind of. Yeah. But is that it?
This is right.
Yeah, square root, right. So I'll just write that. 64. I don't know why it changes pens randomly. Sorry about that. Okay, so then we can determine cosine, because cosine is equal to what? So cosine of theta is what? Yeah, the adjacent side, which is root 64 minus x squared, over the hypotenuse, which is 8. So kind of the point of that is if you end up with an integral, we made a substitution. We end up with cosine as a result. The original integral in terms of x, we have to draw this reference triangle so we can convert from theta back into the variable x. So that's kind of the point of that exercise. Did anyone have any questions on that?
That's just the answer, or?
Yeah, for this particular problem, yeah. Just converting. It's getting us ready to convert from theta back to x.
Algebraically, you could simplify that down to 1 minus x over 8, right?
1 minus x over 8?
Or just be x over 8, right?
Yeah.
So what would you do to do that?
I think I'm doing some wrong math.
Here, let me.
Because wouldn't be integrated.
We could say that this radical, we could factor out a 64 from the radical. 64 times 1 minus. But then we would have x squared over 64, right? We can take the square root of 64, right? So we take the square root of 64 out to cancel with that 8. We can say that's 1 minus x squared over 64. Or 1 minus the quantity x over 8 squared. Sorry, the square root of this. I think that's accurate.
You can't split it into square root of 64 over 8 minus square root of x squared over 8 and then get 1 minus. Oh, same thing, just.
Yes, square root of 64 times, was it 1 minus x squared? This is over 8.
Yeah, I was just turning it into 2 fractions.
Oh, no, yeah. Like that, you mean? Well, we would have to subtract something, right? We wouldn't say this. Right? I'm not quite sure I'm representing what you said fully.
It's all good.
Okay. All right. So the idea behind trig substitution. So we should ask the question, why trig substitution? So what possibly might this help us achieve or accomplish? Specifically, if we think about, let's start with the square root of 1 minus x squared. Just to kind of motivate. So we can't do a u substitution on something like that, right? Because our du is 2x, dx, yeah.
You substitute like a cosine theta for your x, and you would have trig identity?
Yeah, right. That's exactly why. So we can't, there's not a u substitution. We can't integrate by parts. But we do have this thing here. So it's like the difference of squares, but we can't take the square root of a difference of squares either. So that doesn't help that it's a difference of squares, so what? Right? But if we let let's get that over. If we let x equal to sine theta, then what happens is we're taking now the square root of 1 minus sine squared. And what does that do for us?
That makes it cosine squared.
It makes it cosine squared. So it turns the difference of squares with the trig substitution into just a square, which then we can get rid of the square root. Right?
Does that change with respect to x or with respect to theta?
Yeah, exactly. So this turns into cosine squared theta, which is cosine theta. So the idea is that this is hard to integrate, but cosine of theta is easy to integrate, right?
You can do the other way with cosine.
Yeah, right. We could let x equal cosine theta, and then we would have the square root of sine squared. Okay. So naturally, that's not all there is to it, right? Because if I let x equal sine theta, then I also, in my integral, I also have to account for the dx. But I just wanted to show you in a really simplistic setting, why trig functions are used as a substitution. Because it turns the sum of squares or the difference of squares into a square. Right? So let's just go ahead and answer our question. Trig substitutions allows us to change sum of squares and I should have said difference in sum. Difference and or sum of squares into a square. Again, for example, think of this 1 minus x squared turning into 1 minus sine squared, which is cosine squared. That's pretty much trig substitution in a nutshell, how we use it. So you might, based on what we've said here, typically the candidates for trig substitution are when you have like, specifically when you have like the square root of the sum or the square root of difference of squares, or any kind of root sum of difference of squares, and sometimes just sum and differences of squares without any roots involved. So this is kind of, if we were like walking blindly into an antiderivative and we saw like a square root of a sum of squares, then we would probably try trig substitution first. All right. So remember, everything hinges on our original substitution. From here, we would have to say that dx is cosine theta d theta. And so we're adding another cosine theta d theta into the integral. But if we have a cosine theta d theta times this cosine theta, we're just integrating cosine squared as opposed to trying to figure out what this is. Granted, if this also, like if we had bounds on this, it would be pretty easy to determine what that area is. But we're just talking explicitly about antiderivatives. So really we wouldn't, if this were the case, if we had a definite integral here, we really don't need any calculus. Well, we need to know how to evaluate it, but we don't need like any sort of integration techniques, because this represents the equation of a circle, specifically the upper half of a circle, right? So we could just find a definite integral with a lot of these things, not all of them, but a lot of them just by using geometry. So we're explicitly interested in the antiderivative. Okay. So do y'all have any questions? So as you see, we have three different scenarios: difference of square, a squared minus x squared; difference of squared, x squared minus a squared; and the sum of squares. So we'll let this be our theta in each case. Theta. Theta. And we'll have our x and our a for this, a squared minus x squared, or a squared plus x squared. That would be a here, or x, or a and x. And then x squared minus a squared, we have this setting here. Okay. Really, we're thinking about, keeping in the back of our mind, we're thinking about the Pythagorean identities. So when we look at a difference of squares that's like a number minus a function squared, right? A squared minus x squared, or x squared minus a squared, you've got to think of different Pythagorean identities, because a squared minus x squared, what Pythagorean identity would lend itself to turning that into a perfect square for this one? What was it?
Sine.
Sine, or as we saw earlier, cosine, right? So we're thinking about the a as 1. 1 minus sine squared is cosine squared. Here is different though. What trig function squared minus 1? We have to correspond that to what? Secant, yeah. We have to correspond that to secant, because secant squared minus 1 is tangent squared, right? So we're thinking about these not explicitly representing a Pythagorean identity, but what form does it fit into of our Pythagorean identities so that we can rewrite the sum or difference of squares as a single square? Does that make sense? Maybe. Okay. If you're referencing your textbook, they do it a little bit differently. It's really all the same in the end, but just I'm just gonna work this a little bit differently so we don't have like a squared minus x squared. So it's gonna be 1 minus x squared, 1 plus x squared, and 1 minus, or sorry, x squared minus 1. It's really all the same. So here, the substitution with this setting, the a squared minus the x squared, you can use sine or cosine, but the textbook is sticking with sine. So we got to keep in mind that this, what we have on the bottom here, that's the expression involved in the integral. And our substitution is this right here. The x over the a is going to be sine of theta. So if we like start with a squared minus x squared, the way I'm going to look at it, it's slightly different than your textbook, like I said, is we're going to factor the a squared out of both of those terms. So we're going to factor a squared out. So we have 1 minus x squared over a squared. And then we're going to write the x squared over the a squared as a square, x over a quantity squared. Okay, so that's how we'll manipulate a squared minus x squared to look like this. And then from here, there's our substitution. We're going to let that x over a be sine of theta. If this seems weird or you don't like it, then please look at your textbook. From a squared minus x squared, they say let x equal to a sine of theta. And then you have to factor out. At some point, you have to factor out. So I'm just choosing to factor out in the beginning, whereas the textbook factors out at some later point. Do y'all have any questions on that? Does that make sense? Hopefully in light of that little short example we discussed. We've got 1 minus, we want to think of that as sine squared, so we can turn that whole thing in brackets into cosine squared. Okay. X over a here is, our substitution is tangent theta in for x over a. And that could be by itself, right? The a squared plus x squared. We typically, if that were involved, like in an integral 1 over a squared plus x squared arctangent, right? But we're going to think of it as a squared being factored out, 1 plus x squared over a squared, which again is a squared times 1 plus x over a, quantity squared. So if x over a is tangent, we've got 1 plus tangent squared being secant squared. And then finally, this situation x over a will be secant. Same idea, we're going to factor out the a squared. That leaves us with x squared over a squared minus 1. Which is a squared times the quantity x over a squared minus 1. So those are going to 3 here that we've starred this row. That's how we're going to express before we make a trig substitution. steps are they're written out here. They're step 2 is written out as your textbook would have you choose what x is. So just keep that in mind. It probably doesn't make a lot of sense for me to tell you that your textbook does it this way and I do it this way without you referencing it at least once just to see what I mean. Because otherwise it's probably going to sound like gibberish when I say it. Well, your textbook does this thing and blah, blah, blah. It's probably not going to make a whole lot of sense. So you might want to check it out. This is integrate use techniques from 8.2. Okay, so we identify the form. Which one is it? Difference of squares, sum of squares, is the x squared first, etc. And we choose the appropriate substitution. We have to look at our substitution and the derivative of our substitution to account for the dx and the d theta, just like we accounted for the dx and the du. And then typically, section 8.2 with the powers of trig functions, typically those come up quite often when we make a trig substitution. So then we resubstitute. In other words, we take our integral in terms of theta and then resubstitute so we get it back in terms of x. And then that's where this reference triangle comes in, where we have theta, something like that, first example we had, something like that. That translates us from theta back into x. So let's see how that translates. You'll notice here, like maybe, I don't know if anybody's thinking of this, but it might be worth mentioning. So if I take, like in that first example, the square root of cosine squared theta, what should I get? Okay, that's kind of the go-to, cosine of theta, but really what should it be? Yeah, it should be the absolute value of cosine theta. In fact, when the square root of anything squared is the absolute value of that quantity. Depending on where that quantity is, if it's positive or negative, right? So just a really straightforward example, the square root of 2 squared, I know that's equal to 2, but what's the square root of negative 2 squared? Our claim, without the absolute values, the square root of this thing squared should be just this thing. So the square root of negative 2 squared should be this thing, right? We know that's not true. We know this is true, however. So anyways, for what it's worth, the problems in our text are constructed so that we don't have to worry about the absolute value. So I don't know if anybody was thinking that or not, but if you were, you weren't wrong. It's just the problems that we encounter are designed so that we don't have to think about, well, where is cosine positive and where is it negative? Let me split this up into 2 different integrals. Right? That would be very difficult. So we don't have to worry about that. Okay, so evaluate the square root of 64 minus x squared. Before we make our substitution, we're gonna factor out the 64 and rearrange that a little bit. But again, the perfect candidate for trig substitution because it's the square root of a difference of squares. So maybe off to the side, we're gonna do this. We're gonna take the square root of 64 minus x squared. We're gonna factor out the 64 and write it as 1 minus x squared over 64. Square root of all of that. We can take the square root of 64, which is 8. And then we're going to rewrite the x squared over 64 as a perfect square. So we're going to rewrite that as 1 minus x over 8 quantity squared. So that's sort of just like the algebraic preparation for the substitution itself. Okay, so that's our equivalent to the original. Is everybody all right with that? Okay. So we've got 1 minus something squared. We're thinking about what Pythagorean trig identity is 1 minus sine squared, 1 minus cosine squared, right? We want to turn the quantity here into a perfect square.
Sine in this case, right?
Yeah.
Minus sine.
So we're going to let x over 8 equal to sine theta. We have a little bit more work to do, but notice then again what happens here is we've got 8 times the integral, and we have square root of 1 minus sine squared. So the thing under the radical by substitution is now the square root of cosine squared. Well, what's dx? Huh? Not quite. Not quite either. Closer. Notice if x over 8 is sine theta, then x is 8 sine theta, right? So what's dx? 8 cosine theta d theta. So you have to account for the dx's and the d thetas too. So this is 8 cosine theta d theta for our dx. Questions on what we've done? We've got 64 times the integral of square root of cosine squared theta times cosine theta d theta. Right. So then what that simplifies to is 64 times the integral of cosine squared. So that's much easier to integrate than the original function. We've seen the antiderivative of cosine a dozen times, so hopefully you remember how to do that. That's 64. Is everybody okay with where we're at? Cool. We're going to write cosine squared like this. Oops, sorry. Put the 1/2 with the 64. So we have 32. Antiderivative of 1 gives us what? Theta. Antiderivative cosine 2 theta. Okay. Is that what do y'all agree with that? Derivative of sine is what? Cosine. Derivative of negative sine is negative cosine. We have a positive cosine. Sine 2 theta. And then we have some constant here. Yeah? Any questions? So really the hard part's done, right? We found the antiderivative, but now we need to resubstitute in for x. Theta in terms of x. Theta in terms of x now. So what we need is we need to go back to our original substitution. And our original substitution was x over 8 equals to sine theta, right? Our original substitution was that the sine of this angle, sine theta, is x over 8. Let me see, let me go back up here. Let x over 8 equals sine theta. So we go back to our original substitution to draw this reference triangle. Okay. So then what's the base of this triangle?
Root of 64 minus x.
Okay. So we've got our reference triangle to convert our thetas back into x's. But notice this is the sine of 2 theta. And we have the sine of 1 theta is x over 8. So what's the sine of 2 theta?
X over 12.
It's not that straightforward. We have to do this 1/2. Sine of 2 theta, what's the identity for that one? Yeah, right, 2 sine theta cosine theta plus this constant. So now we have theta as an argument. This 2 and this 2 gone. We know sine theta. Sine theta was just x over 8. Do we know theta? Inverse sine of?
X over 8.
Yeah. If sine of theta is x over 8, then theta is the inverse sine of x over 8. And do we know cosine? Yeah, we have the triangle here, cosine. Sorry. So now we've got everything in terms of theta. We can resubstitute. It's 32. Theta was the inverse sine of x over 8 plus the sine of theta, x over 8 times cosine of theta. Cosine of theta is what?
64 minus x squared. Over 8.
There's cosine of theta and plus this constant. That's basically it. We can distribute the 32, but that's the main idea there. Do y'all have any questions? Huh? Were you being facetious? So just this, I know it's not comparable. I mean, it sort of is an analogy to u substitution. This is the step where we get our integral in terms of u, integrate with respect to u, and then from here we've got to resubstitute what u was in terms of x. We're resubstituting what theta is in terms of x from here. So you can see the process is this. I don't know. The story is the same. You got different characters, right? It is a little more complex. Write this out. So here we have we'll have 64, 32 over 64, we'll just have this over 2. Plus 32 times this constant will just give us another constant. So that's our answer. Now it seems like, you know, if we look at this antiderivative and think about, if we take the derivative of this, we get back to the square root of 64 minus x squared. Right, such a simple function has a really complicated antiderivative, right? It's not, I don't know, I don't know, I see that it's not really intuitive. Once we work it out, you can see each component, but yeah.
When you go from the step just above where it's 1/2 sine 2 theta
Mhm.
to the step just down, how do you get to 2 sine theta cosine theta?
Here, how do we get
That
this?
term, yeah, sine 2 theta down to 2 sine
a double angle.
Oh, it's
Yeah.
just a double angle.
Yeah, so yeah, that's sine of 2 theta, the identity 2 sine theta cosine theta. That one shows up a lot in section 2.
Okay.
Do you ever get cosine?
Sometimes, yeah.
Is it the same or?
It's different.
What is the identity for that one?
Cosine of 2 theta, anybody remember the identity for cosine 2 theta?
There's 3 other ones.
There's 3 of them, yeah.
There's 3.
Cosine squared minus sine squared. And then there's 2 more.
2 cosine squared minus 1 and 1 minus 2 sine squared.
Right.
That's impressive. Oh, okay. I knew it wasn't. That was so stressed.
I was about to be really impressed.
I was like, look at me.
Should have blown your cover, Christine.
No, that was not the quadratics one.
All right, let's take a break. You can maybe if you need to just look over that and kind of try to absorb what we've done, and then we'll look at this example after break. Okay. So evaluate the following integral. Why don't y'all give that a shot?
It helps heat up the cavity.
It's just, it was what you were taking that.
Not crazy, so. Anyone know the integral?
Yeah.
I changed that to negative. So like,
Oh, no. I mean, you can, but
would be impressive.
yeah, because what we're trying to do is turn this difference of squares into a perfect square, so that we can take the square root of it. So you want to do this now as like one, this will one side,
Well, yeah.
side, and square, and this whole thing will be cosine square.
Then you can
Yeah, the 1 over the square root of the cosine
Yes.
square. But it only turns into cosine square, 1 minus sine square turns into cosine square if you are x over 60. So, yeah, you only do like this. Because the I think that's yeah, this 1 minus this square to
I have cosine theta, d theta over square root of cosine theta okay, but the rest of it? So there's no okay, so now it's well, now it's there. So now it's
yeah, well, actually, Yeah.
Now, I need to go from there.
Yeah, so I have to get into that. So we leave it out so often, that's what we
You gotta get the cosine theta over cosine sine.
yeah.
Right, especially when you're
Cosine theta, d theta.
So this is square root something else.
Correct. Then we can use
Use substitution. Now I've got down. My notes from my first week in class figure out what you use. Apparently one point from class and forgetting the most important parts of the
Alright, well, you should have
Negative sign That's just one.
Now that we're actually using I'm not straight.
I got here and I just want to put that.
Exam is just like, what is this?
And then give up. For all of these things.
Most of you did trig substitution, which is fine. A few of y'all did recognize that this is an arc sine form, right? So remember the antiderivative of a squared minus x squared with respect to x is the inverse sine of x over a, where our a is 6. So honestly, you didn't need a trig sub for this, but it's good that you did it because, you know, if you forgot that this was arc sine or inverse sine, then the process of trig substitution does get us there. So now we have a different way to look at those antiderivatives that involved inverse trig functions, right? If we forget, then trig substitution can get us there. Right. So our u, before we do that, we're going to write this integral as dx over 6 times the square root of 1 minus the quantity x over 6 squared. And then we're going to let u equal to x over, or sorry, not u, we're going to let x over 6 equal to the sine of theta. Again, we're basing that what's under the radical. We're thinking of this as 1 minus some trig function squared, 1 minus sine squared, 1 minus cosine squared, would turn all of that into a perfect square. That's really the backbone of trig substitution. You got to keep in the back of your mind those trig Pythagorean identities and sort of fit them into what's under the radical. So our x over 6 sine theta, which means dx is 6 cosine theta d theta. We have this 6 cosine theta d theta, or dx. This 6 is still here that we factored out, and this is now 1 minus sine squared. And so we simplify all of that. That's integral cosine theta d theta over the square root of cosine squared, which is just cosine theta over cosine theta d theta. We're just integrating 1 d theta, which is theta plus c. And since sine theta was x over 6, theta is inverse sine of x over 6. We didn't need a reference triangle or anything like that. It's straightforward. And then the ones that do involve the arc trig functions, inverse trig functions, you know, you end up with a theta, and then that's where your inverse trig function will come in, whether that's inverse sine, inverse cosine, inverse tangent, whatever. Okay. Any questions on that? Hopefully you recognize inverse sines when you see them, but if not, this works too. So another example, this one, we see it doesn't involve a square root, but it does involve the sum of two squares being squared themselves. So the integral doesn't necessarily have to have a square root or a fourth root or whatever involved for trig substitutions to work. So let's look at this. We got 18 dx over this thing squared, 81x squared. Let's look at that as, or view that as 9x quantity squared plus 1. You do want quantity squared. You don't want to, look at something like 81x squared or, like 36 minus x squared. We want to view that as, something plus an entire quantity being squared or something minus an entire quantity squared. In this case, a quantity squared plus something. Okay. So now what Pythagorean identity are we thinking about when we see 9x squared plus 1? Yeah, because we're thinking of tangent squared plus 1 is secant squared. Yeah? Does that make sense? So we're going to let 9x equal to tangent theta. In other words, x is 1/9 tangent theta. And then that means dx is 1/9 secant squared theta d theta. Okay, plug in. That 18 is a constant. We can leave it there, pull it out, whatever. So it's 18 times dx, and dx was 1/9 secant squared theta d theta. We have our 9x now being tangent, so this is tangent squared. It's tangent squared plus 1.
Which is secant squared.
Do what?
Secant squared.
Which is secant squared, yep. Okay. Any questions on what we've done, or y'all? Yeah.
1/9 tangent squared.
Say that again.
Because it's 9x squared, the 1/9 tangent theta, or the 1/9.
Oh yeah, we put the 1/9 over here so we could
Right.
keep the
That's where
dx.
you incorporate it for denominator, it's just tangent theta squared.
Yeah, because we have 9x squared, and 9x
Oh.
is tangent.
Gotcha.
Okay, so this 18/9 gives us 2 secant squared on top, d theta, and then 1 plus tangent squared is secant squared squared. So we're actually looking at 2 times the integral of secant squared over secant to the 4th. So what does that give us? The antiderivative of secant squared over secant to the 4th?
Cosine squared.
Yeah. This right here is 1 over secant squared. We don't want to integrate 1 over secant squared, so we're going to call that cosine squared. Again, using the identity, we're going to express cosine squared as 1/2 times 1 plus cosine 2 theta d theta. Those are gone. Antiderivative of 1 with respect to theta. Antiderivative of cosine 2 theta. Plus 1/2 sine 2 theta plus our constant. Sorry. Do y'all have any questions on that?
You're gonna put it back in terms of x,
Yeah.
but sine, okay. Right.
So 1, we've got to draw a reference triangle. 2, we've got sine of 2 theta. We don't want 2 theta. We want theta. So what we're going to do with this again, same thing we did in that last example. Sine 2 theta is 2 sine theta cosine theta times the 1/2 plus the theta. This is going again. This 2 and this 2. Okay, in our reference triangle, based on our substitution was what? Tangent theta equals 9x. We let tangent of theta equal to 9x. So what does that give us with this triangle?
The opposite being 9x, the adjacent being 1.
Right. Yep. The 9x opposite adjacent is 1, which means the hypotenuse would be, yeah. So that triangle now allows us to convert from theta to x. So what's theta? Yeah, inverse tangent of 9x plus sine of theta is what?
9x over.
Yeah, 9x over the root. Times cosine theta. Okay, so there's sine times cosine plus our constant. So notice the denominators here multiplying give us a way to simplify the root. So we have inverse tangent of 9x plus 9x over 81x squared plus 1 plus c. Do y'all have any questions on that? So I really see this section does give people difficulty, so it does require a little bit of work to get the hang of it. I do want to mention, I've got the textbook pulled up as far as how they evaluate it. So if we're dealing with a squared minus x squared, they're gonna go through this process, or they're just gonna say let this x be a sine of theta. So it says, here's their substitution. Just replace x with a sine theta. We're replacing our x's over a's with sine theta, just because we factor out first. And so when they get here with the a squared sine theta, they factor out the a squared. So this is when they start to factor out. And then the a squared times cosine squared. But we've already factored that a squared out. It was the 1/6, right, in that last example. So it's the same idea, it's just a matter of when certain operations are performed. So if you are referencing the textbook, keep that in mind. They do it slightly different. All right, I think we'll end there.